Hi there guys, welcome to this last video on radians, and it's all about small angle approximations. So to start off with, what we're going to have a look at is expanding this, and I know this is binomial expansion, but believe it or not, we can actually use this answer later on. I don't want to explain it then because you'll want to be focusing on the new stuff. So if you fancy, pause the video, have a go, and let's see what we get. So because it's non-integer, we have to use the alternative formula, which I'll write down. So 1 plus nx plus n minus 1 over 2 factorial x squared. So we've got 1 plus n, which is a half, x, which is minus x squared. So then we have a half, take away 1, we have minus a half, 2 factorial is 2, and we have minus x squared squared. So we have 1 minus x squared over 2, that's the easy bit. So what we have here is minus a quarter, half. Well, what's half of a quarter? That's an eighth. So we've got minus 1/8, and we've got minus x squared being times by itself, so that's going to be x to the power 4, so I'm just going to put x to the power 4 up there. Okay, so that will go on, but they're the first three terms. So I'm just going to pop that in later, rather than explain it when we're in this new stuff. Okay. So I'm going to explain some formulas to you, where they came about. I'm going to then show you visually, which makes super sense. It's beautiful representation of them that you'll like. But really, you just need to be able to know the formulas and put them in, and it's actually very easy. But as I'm explaining this, it might, at first it's quite a lot to take in. So we're only looking at small angles, and you'll see why later. So what we have here in this picture, we have two radii, but this radii has been extended, and we've made this triangle here, and we're looking at these values of theta, and it's in radians. You can see that by the little c there. And if we were making an observation here, comparing all the different things we can see, right? So we've got this triangle OAB, this one here. We've got a sector OAC, and if I drew a chord here between A and C, I'd have another triangle. And I think you'll all agree that the one with the largest area would be the first one. So this is definitely bigger than the sector, and this sector is bigger than the triangle. So it's pretty obvious. So we thought, okay, well, let's work out the areas of all of these things and just see where we go. So let's work out the area of this triangle OAB. Right. The great thing about this tangent and radius, we know this is 90. So area of a triangle is just base times height, but we don't know this length here. But because of Pythagoras, trigonometry, we can work this out. So we want this, so let's just call this x for now. And I don't know this length, but I do know this, so let's use these two. So that would be the opposite and the adjacent as the tan ratio. So we know tan theta would be my x over r, so this must be r tan theta. Okay, so the area of this is half the base times the height, so r times r is r squared, tan theta. What's the area of the sector? So the area of the sector is just half r squared theta. There's no numbers to put in, so that's just the general formula in radians. And the area of this triangle is half AB sine C, because it's non-right angled, so let's go half. A and B are both radii, so sine of the angle, so sine theta. So what we can see here is in all three of these we've got this half r squared. So what I'm going to do is cancel those out, so I can say tan theta is greater than theta is greater than sine theta. So this is when it starts to get interesting. So we got to this point and said, right, well, let's see what we can do. So I'm just going to quickly pause the video and write this out. No, I'm not going to do that. I was going to write it out 3 times, but my writing would be too big and it would just look messy. So I'm just going to write it out once. And what we did, we thought, well, what would happen if we divided everything by tan theta? Okay, so what's going to happen here? On my next screen I've got this on a really nice slide so you can see it all in one go, so I wouldn't bother trying to write anything down or worry about catching up. Okay, so that would be 1, yeah, anything divided by itself is 1. Then it can't really do anything with that, so let's just pop that there. Okay, so this is sine theta divided by cos theta, which is sine theta over cos theta. And when we keep change flip, the sine thetas are going to cancel out, so we get cos theta. Right, so we're looking at small angles. So if we look at the limitations when theta is tending towards 0, what happens for cos theta? If you think about cos theta, as theta tends towards 0, it's 1. So what we end up with is that. That doesn't kind of make sense, that 1 is bigger than something which is bigger than 1. Okay, so that's where it starts to get a little bit confusing, but what this means is that they all have to be tending towards 1 for when angles of theta tend towards 0. Okay, so when this angle becomes small, they all equal each other. So what we can say is, therefore, theta over tan theta is approximately equal to 1, I should say. And that is for all small angles. Okay, so because this is approximately equal to 1, then this must be equal to 1. So what it means is theta must be approximately equal to tan theta, because when we do this division it equals 1, so we know that this and this must be the same for it to equal 1. So that is a formula that you will need to know. Okay, so let's have a different angle now. Well, I shouldn't use the word angle, a different approach to the same starting position. So before we divided by tan theta, well, let's divide by sine theta. So tan theta is sine theta over cos theta. So when we divide that by sine theta, we get 1 over cos theta. In the middle, there's nothing really I can do with that. And this is going to be 1. Okay, so let's do the same thing again. So if we look at the limitations when theta tends towards 0, so when this angle is getting towards 0, we've got cos theta is going to be 1, so 1 divided by 1 is 1, and that's greater than theta over sine theta. So we have that same situation again. So what we can say is, therefore, theta over sine theta is approximately equal to 1 for all small angles, which means theta must be approximately equal to sine theta, because when we divide these two things it has to be 1, so they have to be the same. So this is also true for small angles. Now the next bit is a little bit trickier, so let's just change colour again and just try and write it down here. So tan theta, like I said, I've got this all on a nice screen in a second. So tan theta is greater than theta, which is greater than sine theta. Right, so we've kind of got to go for a different approach here and use some of our identities. It's just divided by theta, there's nothing we can really do. So we know cos squared theta is equal to, or identically equal to, 1 minus sine squared theta. So cos theta must be this, yeah? So if we square root it, so we've got that. Well, for small angles, we know that sine squared theta let me think about how I'm going to say this a second. So using this here, what we can say is, this is sine theta times sine theta, right? So sine theta squared, we just write it like that so we don't get confused what's actually being squared. So sine theta for all small angles is approximately equal to theta. So what we can actually say here is that we can only say this when we're looking at small angle approximations. It's not some new identity you can use in any other example. Right, well, if I could rewrite this as that, and that is what I asked you to do at the start. So if we look at the first three terms, we know this is the same as that. Okay? But then if we do the same before, if we look at the limitations of theta tending towards 0, well, that's going to be so small, we're going to ignore it. So what we would have is 1 minus theta squared over 2. So I've just got to move this down a bit. And that, don't forget what we're doing here, we're looking at cos theta. So these are all cos thetas here. So this is cos theta, cos theta, cos theta. So if we just ignore this last term here because it's so small when theta tends towards 0, what we end up with is that. So this is another formula you just need to know. And if we go to the next slide, you can see them all here. Okay, so you could pause the video and maybe digest everything I've just said. I just went through this basically. And you just need to know these three formulas written in black here. And I've popped in here in pink just some examples. So if it was sine 2 theta, that's approximately equal to 2 theta when small angles. Tan 3 theta, you can see the 3 theta is approximately equal. And the cos, that's when it starts to get a bit harder. So cos 2 theta would just be 1 minus 2 theta squared. So you've got to remember to square it, but the actual trig ratio is going to disappear. Right, so if you're watching this thinking, what is he talking about? You just need to know the formulas. And I'm going to show you this because it explains it beautifully. I just want to make sure I've got enough in the window. Right, so here's a sine curve. So the blue is the sine curve. And what we're saying is that sine theta is approximately equal to theta when angles are small. So if I change the size of theta, you can see for all of these values, it's pretty much identical to that sine wave. It's only when theta becomes, you could say 0.9 is still small, but we're talking about really small angles here. So we're talking, anything below this sort of level here. And for big angles, you can see, well, it's a really poor approximation, okay? But for tiny angles, it's a very good approximation. If we look at the cosine graph, you'll see I've drawn in red here the 1 minus theta squared over 2. So you can see that's a very good match to the cosine curve when we're looking at small values of theta. If we were to draw the theta line, obviously that wouldn't be a match at all to cos theta. Yeah, it would be in this sort of direction. And again, when we make the angles, still small but not tiny, so as soon as they get bigger, you can see that this as an approximation is useless. So for small angles, that's there. And the tangent one, again, we're saying tan theta is approximately equal to theta. When x is really small, you can see it's pretty good estimate. But when it gets bigger, it's useless again. So hopefully that visual has made you happier, and what you basically need to know are these three formulas written in black off by heart. Okay, so let's have a look at some examples. So the first one actually is the harder one. So what is cos 2 theta approximately equal to? Well, that's just equal to 1 minus 2 theta squared over 2. Okay, so remember cos theta is approximately equal to 1 minus theta squared over 2. So I can lose the ratio, but whatever my angle is, I'm squaring it. And then I've got take away 1. And we've got theta, but sine 3 theta is going to be equal to just 3 theta. So if we tidy this up, the 1 take away 1, that's going to go. So what do we have here? We've got minus 2 theta times 2 theta, that's going to be 4 theta squared, but then we're halving it, so we're going to get 2 theta squared. Theta times 3 theta, like x times 3x, is no different, is going to be 3 theta squared. So this is approximately equal to, theta squareds are going to cancel, minus 2/3. Again, number 2, this is a little bit easier, this one. The first one was definitely the hardest. So small angle approximations, we can see this notation here, so we can identify the topic. So we know that sine 3 theta is equal to, well, approximately equal to 3 theta. And the sine and tan ratios, they're the easiest, you can just lose them. It's only the cos that you have a little problem. So we've got 8 theta divided by 4 theta. The thetas are going to cancel. That's approximately equal to 2. Okay, so no cos. So this again, it's pretty easy. So that's going to, the sine theta, or sine x, it doesn't have to be a theta, it could be whatever we put there. But for small angle approximations, that's approximately equal to 5x. So we have 5x take away x. Tan is the same, so we can lose the ratio. And we're going to end up with 4x over 2x. The x's are going to cancel, and that also is approximately equal to 2. And the last one, again, no cos. We can't do anything with the x squared, so that's x squared. Sine 3x, we can lose the ratio. 2x, can't do anything with that. The tan, we're going to lose the ratio. So that looks like it needs to be factorised, so let's do that. X brackets x minus 3 all over x. The x's are going to cancel, so this should be curly approximately equal to x minus 3. Okay, so hopefully when you did the examples you saw it's a pretty easy topic, but understanding where the formulas come from, that's the difficulty. Do you need to know that? I'd say yes, but the most important thing is that you know the formulas off by heart. Okay, best of luck everyone. Oh, wrong button.